Hello again. We continue our analysis of point patterns with now a focus on this concept of intensity that I mentioned the other day. And specifically, we're going to look at how intensity is measured and how it changes with the use of a particular bounding polygon for the point pattern. Then we move on to a brief discussion of the notion of complete spatial randomness and the associated Poisson planar distribution of that is the main tool to assess what happens under the null hypothesis, and finally some brief remarks on how to simulate a spatially random process. And let's start with intensity. So intensity, the average intensity, is referred to as the first moment of a point pattern distribution, or characteristic of the point pattern distribution, of the spatial distribution, and is very simply the number of points per unit of area. Now, what the unit of area is will of course depend on the particular application, but it's very simple. The intensity, lambda in my notation, is the number of points n divided by the area. Now the catch is that the area depends on the bounding polygon. As we saw in the previous lecture, the points can be floating in space, but we have to somehow constrain the area of interest. What is the interesting constraint within which the pattern of the points will be studied? And that is the bounding polygon. And there are several different notions of how to define this bounding polygon. In a lot of the classic examples, and also some of the data sets that I showed previously, the Swedish pine, the Lansing woods, those kinds of data sets, the bounding polygon is a square, and typically set as a unit square just to make measurement easier. Obviously that's unrealistic, but it is the standard used in many classic example data sets. A more realistic boundary is the actual regional boundary, typically determined by means of a GIS. But there's also two other notions of the bounding polygon that are very common and very common in the point pattern literature, mostly developed pre-GIS, is the notion of a bounding box and the notion of a convex hull. So, very simply, the bounding polygon, using our Chicago supermarket example, is the city boundary. And so we have, as we saw earlier, the points floating in space in the sense that there is no network, but yet bound by the outline of the city. The second notion is the notion of a bounding box or bounding rectangle, which is a rectangle around the points with the axes, with the sides parallel to the axes, and basically taking the most extreme point on the right and the most extreme point on the left, as well as the lowest and the highest point. So the lower left corner of the bounding box is the smallest value for x and the smallest value for y. The upper right corner is the largest value for x and the largest value for y. And these don't have to be actual point locations. In fact, typically they are not. Just to illustrate this again for our Chicago example, and right away you see a big difference, namely, in the city boundary, we cut this off at the lake. This is the lake, but here the lake is part of the bounding rectangle, the bounding box. So let's see, the lower left corner is minimum of x, the most extreme to the left of x, and also the lowest of y, so minimum of y. Then here on the upper right corner, we have the maximum of x, the rightmost point, as well as the maximum of y. So this rectangle is the bounding box, and now we're going to measure intensity as the number of points relative to the area of this bounding box. The third notion is a notion of a convex hull. And the easiest way to think about a convex hull is imagine your points as being pegs that stick out. And you have a rubber band, and you move the rubber band around the points. Then the tightest fit around the points, that is convex, is the convex hull. And there are a number of different ways to compute that. We won't get into that. That's more of a geocomputation, GIS feature. But just to illustrate, this is what the convex hull looks like for the Chicago point. So one thing that it has done is that it has gotten rid of the lake, which is over here, by tightening around the most extreme outermost points. There may be a little bit of lake around here, but the biggest effect of the lake has been corrected for it. So this is the tightest possible fit. Now, one drawback of this particular approach is that it does include actual points as on the boundary. So for some statistical analyses, this is not that great an idea. So there have been some adjustments, simple rescaling of the bounding box and the convex hull. And the most commonly used one is called Ripley-Rason transformation. And in essence, it pushes out the bounds of the box or the bounds of the convex hull using a particular ratio that is a function of the area inside. And we won't get into technical details. Just to give you a sense, you see very clearly here how the convex hull is kind of pushed out a little bit. You see from here over to there, and then similarly with the bounding box, it gets pushed out a little bit. So what that means in terms of the computation of the intensity is that the area of the bounding polygon is enlarged. So same number of points, larger area, lower intensity. And just to illustrate the effect of these different bounding areas on the computation of intensity, we have 149 points in our Chicago supermarket example. And we can compute the area for the three different cases with an adjustment for the bounding box and the convex hull. And we see the results in this slide. So for the actual boundary, the intensity of the average number of points per unit area is 2.31. For the bounding box, it's much lower. It's 1.55. Now, why is that? I mentioned the lake. All this empty space is included in the denominator, but the numerator remains the same. The numerator is 149, but the area is much larger. So therefore, the intensity must be much lower. The highest intensity we get for the convex hull, which is the tightest fit. So in a sense, the smallest area, convex area around the points. Then when we do the adjustment, the Ripley-Rason adjustment, we see that the intensity is a little bit lower for each of the cases. For the bounding box, it goes from 155 to 151. And for the convex hull, it goes from 253 to 234. And that is as I mentioned, the consequence of increasing the area just a little bit at the edges. So this is the notion of average intensity, and that has direct consequences for how we formalize the concept of complete spatial randomness. But as I mentioned earlier, the complete spatial randomness in and of itself is not that interesting because it's not a very realistic process, but it's a great standard of reference. And it's in essence the conceptualization of a uniform distribution in two different ways. And it's important that it's not just one aspect, it's both aspects. So each location has the same probability of having an event. So the risk surface, if you think of it that way, is uniform, is the same everywhere. but also the fact that there is an event in a particular location does not affect the probability of having an event in the other location. So the events themselves are independent. So these two together define what is called a homogeneous planar Poisson process. And if you recall your statistics, whenever you say Poisson, there's a particular distribution associated with that, and that is a distribution that we will use to formalize this homogeneous Poisson point process. So we're looking at the distribution of how many points would be in a given area following a particular intensity lambda. And as we saw, the lambda average intensity is the number of points over the area. In our previous example, that was 149 over the area of the bounding polygon that we used. So in other words, n, 149 points, follow a distribution characterized by an average number of points, which is the intensity times the area, and a Poisson distribution. So the number of points in a particular area follows a Poisson distribution with the mean equal to lambda times the area. And hence the attractiveness of using a unit area in a lot of the classic examples. Then you don't have to worry about this part. You just have to worry about lambda. But the essence is that for a Poisson distribution, there's only one parameter because the mean and the variance are the same. So once we have this parameter, this intensity, the average number of points we can expect in any given area, then we can compute the probability of having 1 point, 2 points, 3 points, and so on in any given area using a Poisson distribution. And that's the essence of the use of the complete spatial randomness notion. So just to recap, refresh your memory, Poisson distribution, only one parameter, the mean. In our case, that mean will be the intensity times the area, or the average number of points in the area. And for a Poisson distribution, the mean equals the variance. If the variance is larger than the mean, we call that over-dispersion. If the variance is less than the mean, we call that under-dispersion. But for the Poisson planar process as the null hypothesis, the mean and the variance are the same. So then the expression for the probability of finding y number of points in a given area. So we have a given area and we want to know, well, what is the probability that we have 0 points, 1 point, 2 point, and so on. That is found by this expression, the exponential of negative of the mean. So it's a negative exponential. Then the mean to the power of the number of points divided by the number of points factorial. So this is classic Poisson distribution. What is of particular interest, and we'll see why later, is to compute what is the probability of having no points in a given area. And that's very simple because we just replace y by 0, and then in essence this part disappears, and all we have is a negative exponential of the average number of points in the area, negative lambda times the area. So that's very important for later on. For example, later we will be dealing with nearest neighbor distances. So think about what a nearest neighbor means. That means that you have a point and its nearest neighbor, and in a circle around this point, with the radius equal the distance to the nearest neighbor, there are no points. And so that relates directly to this Poisson distribution, especially this expression here, which could give us the probability of having no points in that particular area, given the intensity of the process. So that's how it all hangs together. And just to refresh your memory, The Poisson distribution for, for example, mean 2, you see is very skewed, but as the mean goes up, it becomes more and more symmetric, and it can actually be approximated by a normal distribution for larger values. So just to illustrate this concept again, let's say we have a complete spatially random process, a planar Poisson process with an intensity of 5 points per unit area. Let's say we have a circle. The area is pi r squared. If r squared is 0.01, pi is 3.14 still. The area is about 0.03. And so then, using our previous expression, the negative exponential gives us the probability of having no points in this circle, and that's, as it turns out, for those particular parameters, is 85%. So this gives us a way of figuring out what is the probability of having a certain number of events in a given area with a particular intensity of the process in mind. And now we can use this concept to construct what is called a probability map. And this is due to Choynowski. It's actually a fairly old process, but it has its flaws, but it's actually very intuitive. Basically, what you do is you take the intensity of the process, and we've computed this for the Chicago stores, and then given that as the mean parameter for a Poisson distribution, we can figure out for any area what is the probability of having the observed number of events in that area. So let's say we have a mean intensity of 10 events per unit area, and we have a given area that is twice the unit area. On average, we would expect to have 20 events in there. That's what the notion of average is. So what if we have 50 events in there? We can compute the probability of having 50 events. And if that probability is small enough, we say this is significant. So we're going to map the areas where we have either way more or way less events than we could expect given the average intensity of the process. So think again of the Chicago supermarkets. We have 149 of those. We can figure out per square kilometer or per hectare what can we expect to be the average number of supermarkets in that area. So we have, say, a community area. We compute its area. Given the intensity of the process, we could expect, say, 20 supermarkets, but we have 2. What is the probability of that? We plug it into the Poisson distribution. We get the probability. Let's say it's 0.0001. We say, hey, wait a minute. This is highly unlikely given the average intensity of the process. So that's the idea behind a probability map. And you'll see an example of this in the notebooks. We'll do this in the lab. But it's very intuitive. It gives you a map like this for the supermarkets, where the dark brown ones are the areas that are significantly below. So one of them is, if you know Chicago, this is O'Hare. This is the airport. There's no supermarkets in there. So, what is the probability of having no supermarkets in this area given the average intensity of the process? And then in these community areas, we have more supermarkets than we would expect for the average intensity for the whole map of Chicago. So that's the notion of a probability map. Very quick and dirty way to find, in the context of how I put it, interesting locations. So these are locations that seem to not satisfy our initial assumption of a fixed uniform intensity of the process. So we have to be careful with this, because supermarkets are not located in function of area, but they're located in function of where the people live, and especially in function of where people with money live. So using the area is not necessarily the proper reference for the population at risk. And the way we have calculated the probability map here, we used area, but of course you can use anything else as long as it is a Poisson distribution. It also ignores spatial autocorrelation. Remember, we posited that one of the fundamental assumptions of complete spatial randomness is that the existence of a point in one location does not affect the probability of a point in another location. So if that is not true, if there is spatial autocorrelation, then these probabilities are off. And one thing that it can do, and that it's actually useful for, is suggest that maybe the assumption of a uniform planar process is not the correct assumption, and in fact, instead, the point process is not homogeneous or inhomogeneous, as it's sometimes called. So that's how we use the notion of complete spatial randomness. And then just very briefly, how do we simulate this? There's actually a very large literature on how to do this, and how to do this with many different non-CSR processes. But the simplest way to do it is for a fixed number of points. Let's say you have 50 points. You just randomly generate coordinates using a uniform distribution on the length of the horizontal and the vertical dimensions. So if we have a unit square, that would be a uniform number between 0 and 1. If we have other distances, we just scale it up or down. And so then you get something that looks like this, very easy to do in SpatStat, for example, but we won't get into that here. But you have the number of points, and you just generate random uniform numbers and plot them, and that's it. And you can do this many different times and then figure out, well, what is a spatial distribution of or the distribution of a particular statistic under spatial randomness. Let's say we would look at, and this is just an example, let's say we pick this little box and we compute the intensity of the points in this box. So if we do this, for just one replication, it may not match the average intensity of the process that closely. But if we do this many, many times, then we'll see the distribution of this average intensity in this little box converging to the actual population intensity. And that's one way to get a sense of how much randomness is in the process, even for a process that has no structure whatsoever. So CSR is great as a frame of reference, but as I mentioned a couple of times already, it is not a natural process. Very few processes are actually like that. It's also, because it's purely random, it's not interesting in and of itself, and so it's used as a reference, as a null hypothesis. One aspect of it that I alluded to a little bit is that it's very easy to simulate, so it's going to be very attractive to do things like permutation tests or randomization inference in point patterns. And because the analytics in point patterns are often extremely complicated, that is typically the way we carry out inference, by using the simulation of a random spatial process. So we moved ahead a little bit in spatial processes, spatial point processes, particularly focusing on the notion of intensity, which is the average intensity of the process, how we measure that, how it's sensitive to the definition of the bounding polygon, and then how the notion of intensity is used as the parameter for the mean in a Poisson distribution, which characterizes a homogeneous planar Poisson process, which is the formal expression of complete spatial randomness. And we closed with just a few concepts of how to simulate a CSR, a complete spatially random process. Next, lecture, we deal with visualizing intensity. See you then.